Hello everyone. Now I am going to present the advanced semiconductor physics class final exams question solution. Myself Selim Reza. My student ID is 2021160207 and my academic advisor is Professor Jae-Yong Park. The first question is the draw the arrow according to the below condition. With this reference figure, we need to draw this figure, the whole and current direction. So we know that the diffusion flux always depend on the concentration gradient, does not affected by the electric field. So the this one is the high concentration and this one is the low concentration. So electron and hole will be diffuse this direction. That means right to left. Electron will be diffed will be this direction. A hole will be dipped this direction, and the current direction will be the same direction of the hole this direction, but the electron current will be always opposite direction of a electron the electron path follow. So if the electron diffuse this direction, the current will be the in opposite direction. And if we go for the electric field is always affected by the negative charge. So the negative charge of electron, it will oppose. If the electric field is the direction, the electron will be the go this direction. This one is the drift current, and it is the drift flux. The drift flux will be this direction. And if the electron will drift in this direction, so current will be in the opposite direction, this direction. And hole does not affected by the concentration of hole electric field. So if the electric field is goes direction, the flux of hole will be go this direction, and the current will be the follow the same direction of hole. And the second question is draw the energy band diagram for accumulation, depletion, and inversion mode of the p channel using MOSFET. So if we go for the accumulation mode, that means the first figure we can see the metal and oxide layer and the semiconductor layer. This band gap is tilting like this in the accumulation mode. Basically, the accumulation mode is defined by the majority carrier of a hole, and for the depletion mode, if we go for the depletion mode, it will conducted by the weak inversion. Weak inversion, you can see the for the depletion, it will bending the band diagram will be like this one and this one, and the Fermi level will be the follow the same state, will be the follow the same state. And for the inversion mode, it will conducted by only the minority carrier of the electron. So it will more inversion in the minority carrier of electron in this same. And we can see this one, and it will tilt also same like this, the bending in this direction. And now the how to draw, the second question is how to draw remove the conductive channel at the VGS is 0 in the reference figure. You can see in this figure the P plus and P plus, that means this channel is P, and this one is body and this one is a gate. So how to remove this P channel? So we need to we need to remove from this figure. We can see the P channel is created between source to drain. So this P channel is removed by if we apply the positive bias in the gate terminal. So the electron will be pulled, and the depletion region will be removed from the conductive channel. So this one will be removed by the applying of the positive bias in the gate terminal. And the next question is explain the mechanism why the current of the saturation region is always constant. So first we consider for small VGS, we applying for small VGS. So if we apply small VDS, that means source to drain voltage. If we increasing small, the electric field is increasing. That means the electron velocity also increasing, and if the electron velocity increasing, the current density also increasing, and the current also increasing. But it is not always valid for all. So it is valid only for when the movability is constant. So from this we can say that the velocity is depend on the electric field and the movability. So if we increase the electric field, the velocity also increasing, and the movability is a function of electric field. So the if we apply the electric field which is greater than which is less than 10 to the power 3 volt per centimeter, then we can say that the electron mobility is constant. We can consider that one. Or if the electric field is 10 to the power 4, 10 to the power 4 to 10 to the power 3, between this range, we can we need to be consider the electron mobility will proportional to 1 by e to the e root. And if we consider if we apply the electric field 10 to the power 4, then we need to consider electron mobility is 1 by electron mobility is 1 by electric field. So if we apply the large VGS, if we apply increasing the VGS applying, so we need to be consider the mobility is 1 by electric field. That means if we apply more VGS, the electric field will be the also increasing. But we know that the velocity for this one is constant, so the current density will be the constant, and the current density means the current is also be constant in the saturation region. You can see if we apply the 0 to 6 voltage, it will firstly increase like this one, and after that a pinch of point it will just follow the saturation region in the constant current, because of the velocity is constant in this region, or movability is follow 1 by electric field. The electric field is increasing, so mobility is decreasing. That means the velocity and for this constant, so current is also in this region is making a constant. And the next question is, draw the energy band gap of equilibrium and saturation mode of MOSFET. So for the equilibrium mode, if we consider this one as one semiconductor and this one is channel, and this for the another semiconductor, or it can say that a source is source channel and this one is drain. So the band diagram will be the red color. Show the red color for this region is the at the initial position or equilibrium position. The Fermi level will be this. And if we go for the saturation region, that means the current density is always high, and we know that in the saturation region the current high means the high drain to source current, high to dense source current. And in this condition the band diagram will be bending this one, and the current will be drift this follow this path, but in this region the current will be uh, constant or saturated region. So this one is the band diagram for equilibrium and saturation mode of MOSFET. And why, the next question is why the transconductance, that means GM, in saturation region is affected by the gate to source voltage, not drain to source voltage. So if we know the transconductance GM is equal to 1 by the resistance, 1 by the resistance. So and the current, if we conductance can be change of current of drain to source and voltage of gate to source. So this one is definition of transconductance. And in the saturation region, if we go for the saturation region, this region, the current equation is IDS is saturation is W, that means channel wide mobility of carrier, and the oxide oxide thickness, and this one is channel length, and this one is voltage for gate to source, and this one is threshold voltage to the square to the threshold voltage. But if we from this one we can drive the transconductance, it will be draw this. You can see that there is a no any VGS controlling this equation, and we know that in the saturation region this current, the current drain to source current in the saturation is always constant, so it will not change. So transconductance will be only change with this VGS of change. If we change the VGS, this will be the transconductor also increase change. If we increase this one, that means VGS. If we increase, the transconductance will be decrease. And if we decrease VGS, the transconductance will be the increase. So we can conclude that transconductance change only as a function of VGS, gate to source voltage, and it is independent of VDS. And the next question is, what is the difference between the acceptor like state and the acceptor level? If we go for p-type semiconductor, the acceptor level is uh, close to the valence band and below the Fermi level. This one, this state is called as the acceptor level. Basically, these acceptor level are um, normally unionized. It is not any ionized by anything. So it is normally unionized acceptor. But if we go for the metal oxide and semiconductor interference, in the interference we also saw the same like a state, and this state are called as the acceptor like state. But this acceptor acceptor level and this acceptor like state is basically defined, it is neutrally empty or empty, but when it occupied by the negative charge, it will full by the electron. It will be show as a negative charge when it full by the electron. That is the basic difference between the acceptor level and acceptor like state. It will found in the metal oxide and semiconductor interference, and this one found in the intrinsic semiconductor or extrinsic semiconductor below the Fermi level. And this one basically the normally ionized, and this one is normally neutral, or it it may be when it the one electron will be occupied, this will show the negative charge. The next question is uh, the degradation mechanism of the uh, semiconductor. So by the applying in the under of the plus VGS stress. So you can see in this figure, if we apply some voltage, let's say 10 voltage in the initial condition, and after that we will get the minus 10. It will be the opposite. It will be the opposite same. We can found it here. Charge will be created, and the no charge will be trapped into the interference. But after 2 or 3 days later, if we say that the charge will be the here 10, and it will show the 6, that means this interference is trapped by -4. So if we need to be get the same performance of the initial position, so we need to be apply the positive bias stress for the n channel. So if we apply here the 14, we will get the same performance of the before of the initial state. You can follow this graph. If IDS and VGS, the first graph is denoted at the at the initial state, but after 2 or 3 days it will show this graph. That means we need to more VG voltage to get the acquire the same performance. So that's why we need to apply the positive bias for stress for getting the making the same performance, and this is called the make the degradation. So once we apply VGS in the N MOSFET for the stress of the bias, the accumulated electron from N channel will be trapped into the trapped into the this silicon oxide or silicon interference into the silicon oxide interference. And after that, if we apply after that, VTS is positive shifted. It will positive will be positive into the shift. It will, you can see the positive will be the shifted when the operating, and make the more uh, make the more degradation of the device. So this is the positive bias for n channel degradation. And why for the why we take the more serious of electron carrier effect, hot carrier effect for hole, less serious than electron. So you can see in this diagram, basically there are some causes for which we do not take the hole carrier effect for the hole, hot carrier effect for the hole, not serious, so as serious as the left side figure. We can see that the barrier for the electron is almost 3.1 electrovolt, but for hole it is 5. So it need to, if need to be hole overcome this barrier, it need to be more energy. But if for the electron it is less, so if we apply the less energy, the electron will be more the more energized, and it will go through this way. So we need to, so the whole need to be the more energy and overcome the this barrier. And but for the electron it is the less energy. So always we need to be think about the electron, not less than the whole. So that's why in the hot carrier effect, we need to be think about more about electron less than the whole, for because of the band gap. The band gap here is the whole band gap is large, and the electron hole gap is band gap is less. And they explain what is the causes of role of phenomena. Basically, when the channel length, if we reduce the channel length, the electric field will be the higher and higher and higher. So the VTS will be become smaller, smaller and smaller. If we change the length change, length decreasing, and it also increase the electric field, increase, and the VTS will be the decrease like this one, and it shifted to the VTS in the negative direction, and this phenomena is called as the threshold voltage roll off. So threshold voltage is roll off. So in the short channel device, the drain to source depletion region enter further into the channel length and depletion part of the channel. Due to this, the lesser gate voltage is required. So it so means if we for the short channel, the if the VTS is less, that means we need to be less voltage to need to the turn on the device. So if less gate voltage required to invert the channel to reduce the threshold voltage. So this phenomena is produces by actually if we apply the high drain voltage, it will be created in the roll off position. And the reduction of the threshold voltage increases the sub-threshold voltage leakage current, and the sub-threshold voltage leakage current is inversely proportional to the sub-threshold voltage also. And the next question is, explain the mechanism of low VTAs in terms of charge sharing. So we know that the threshold voltage is the minimum gate voltage ap- applied to the get to the source to turn on the device. That means for channel creation. VTAs, if the VTAs is decreased, the low VTAs, that means if we VTAs is decreased, the for the with the length for the short channel geometry of MOSFET, the electric line of force is perpendicular to the equipotential contour. That means this one and this one, electric field. And the depletion charge that is physically underneath attention into the approximately triangular region near to the dead source, and their electric line terminated not to the gate but instead of drain and source. You can see the red region is not more affected by the drain and source. The rectangular shape of the gate depletion region in this absence of the drain and source effect. We cannot any effect in this region and for this region. So here is the charge sharing method is going on, the depletion region and the electric and the electron and hole share by combination and make this region, and no effect from this electric field. And once this depletion charges should not counted into the VTA's expression. This charge will be the depletion region changes. This one is depletion region. So this region was not counted into the VTA's expression. So clearly for the long channel device, the triangular region of the charge region near to the drain source very small fraction. This one will be for long term device is very small fraction. So the total depletion charge underneath of the gate. So the gate will be the tuning this channel. So it is not less effective for the long channel. But if we go for the channel length reduce, this channel length is reduced and reduced. The resulted, we can see that if we reduce and reduce the role of phenomena as a function of length. So it is important because it is hard to control the channel length specified by manufacturing. So we cannot control this length, um, the role of phenomena here. So the channel length variation lead the problem of the control of a VTAs, and this charge sharing of the deflation region and the charge sharing will be cause a problem and to the end, and also the depletion region to control make a problem with the control of a VTAs, and the channel also reduce this part, the red part, like this. And the next question is how the VTAs become less and negative and negative. So what will be the problem? If we go for the VTAs going for the sub-threshold level, we expected some leakage current. If we go for this from this to the basically the threshold voltage is ideally follow this track. But if we go for low threshold voltage, it will be show the more leakage, and that means we need to be make a make more energy to turn on the device. So this will wasting standby the power dispersion. If the threshold voltage is lower, then is it good? Isn't it good? Because the device is operated with less power. But if we think that, of course, it is true, the device can driven with a less power. However, it is a fatal disadvantages in the off current increases when the threshold voltage decreases. That means if we go for the negative region of the threshold voltage, the off current, that means the leakage current of will be increased. So the if the threshold voltage decreases, basically the MOSFET have a leakage current that is called as a sub-threshold current, sub-threshold. So when the in the off state, the VG is low, that means gate to source VG is low, then the threshold voltage, a, a minimum current flow. And if the off current increases, the leakage current standby also increases. So this will make a power dissipation into the devices. So it is not good for the device. And this, if we go for the VTA is also variation, that means threshold voltage variation. So the threshold voltage variation will make a VTA's role of phenomena and drain induce lower bearing phenomena, and also a hot carrier effect phenomena also by the these VTAs also if we variation. The next, how to reduce um, the hot carrier effect into the semiconductor. So if we know IDDL, or that means lightly doped drain, is a buffer to reduce the impact of the hot carrier electron. In this region, we apply this one is for drain, this one is drain, and this one is source. We apply a small lightly doped region into the in lightly doped near to the source and drain, because if we lightly doped, we know this one is highly doped and this one is lessly doped, and so lightly doped structure, and this one is conventional structure which was not um, for considering the hot carrier electron effect. And we can see this, it is only for the highly doped source or drain. If we add a new LDD, that means lightly doped drain here, so it will shift it the energy level here, and this one is for source drain, and it also reduce the maximum electric field. It will reduce the maximum electric field. We know that if we add additional lightly doped region into the source or drain region, drain gate region, this region make will the depletion region will be make wider and wider. So like wider at the reverse direction, at the channel direction, and it will the reduce the electric field. So electric field is directly connected with the hot carrier electron, hot carrier effect. So it will basically reduce the hot carrier electron if we apply the LDD region into the drain and source by reducing the electric field. So how to reduce the DIBL, that means days induced barrier lowering? If we know the for the small channel length MOSFET are, if we scale upping, that means if we not properly geometry properly, the source and drain junction are too deep and channel doping is too low, that will be unintentionally interaction between the source and drain, and this is called as a drain induced barrier lowering. As the drain bias is increased, if we increase the drain bias, the conduction band is of the drain will pull down and the drain channel depletion width will be expanded. The depletion region will be expanded like this one. It will be expand and expand and it will be expanded and expanded. For the long channel, unless the gate bias is increases, the lower it the potential barrier. So there is a little drain current. So it is not affected. But for short channel MOSFET, the drain bias is increases, the conduction band is of the drain is pulled down and the source channel of the potential barriers is lowering down due to drain induced barrier lowering. That means if we apply the increases of drain, it will pull and it will be increase and increase like this one and this types. So we need to prevent. So what is the solution? So the problem will be mitigate by applying a substrate reverse bias, because that reverse bias potential barrier will be end into the source drain. So source and to the drain, or the source or drain junction maybe might sufficiently shallow. That means scale properly, or as the channel length is reduced, it prevent IDBL and DIBL. So channel doping must be significantly high to prevent the drain from the beginning to control the solution junction. This can be achieved by forming a anti-punch throw implemented into the channel. It's called halo, halo doped region into the lightly doped region. After that, this region is green region. This will affected um, the drain induced barrier lowering phenomena. And now, what is the pros and cons of the halo and IDDL? So if we apply the halo, so definitely it will reduce the drain induced barrier lowering. And if we apply the lightly doped drain beside the source and drain, it will be overcome the hot carry electron. So these are the two advantages of the halo and IDDL layer. But everything has positive and negative effect. So its negative effect is it reduce the effective area. It's occupied the more area for these two region, halo and ADDL region. And on the other hand, it also increases the capacity effect. That means capacitance of resistance is also increasing. This is the disadvantages of the halo and IDDL. And next one is describe your expression for this class. So I like to thank Professor J.O. Park and also Professor Namyam King. And I really enjoy this course. And I think this class is well planned and layout is too good and easy for understanding for every student. And I actually enjoy much of this, enjoy very much of this course. And I took this course, Advanced Semiconductor Physics, willingly, so that the first couple of weeks I found that its homework is really good and very cool and very innovative. And that's why this is my second semiconductor reading course. In my undergrad, I also took a course, but it was not so interesting. And I would like to say that it's really enjoyable for these times by the conducting by the Professor J.U. Park. And the PPT designed also great. And I thought that the course is very informative and supplemented for the reading. And the picture was graph and really help for me get a idea what I am study. And I think the simplicity of this course, that's why I really enjoy it very much. And I understand how well to help, and this will be help to the other student to informative and maintain it. And the assignment in the beginning of the semester really relatively long, but I thought everything is fair and then question was very well presented. And the one thing I dislike about this course is beginning of the semester, the course time is different from the other course time. And I think your grading is very well done, and professor doing very well, and I enjoy this taking advanced semiconductor physics, and this was the opportunity, and I am a lucky guy to conducting or to achieve this class from Professor J.U. Park. And thanks again to Professor Namiam Kim. And what is the takeaways from this class? Basically, the most beautiful thing of this course is I really like this one. The professor tells the the whole class like is storytelling from basic to advantage. Uh, and this thing is make me more and more enjoyable for this class, and may take me the to attracted to the semiconductor. And I really true that I never knows about the Fermi level, uh, and Fermi distribution function by the fluctuation of concentration. I just learn from this class very clearly. And I also do not know about how the origin of band gap into the between the conduction band and valence band. So I really acquire from this class. And I also learned the fundamental semiconductor physics, of the what is the semiconductor and how the energy band gap is origin and Fermi distribution function and Fermi level in the band gap, and electron hole concentration with a conduction band and valence band with a temperature variation, concentration variation, and how we can make the N type and P type doping, and the concentration variation can happen into the semiconductor, and how we can make the industry by compensated or degenerated semiconductor. And I also learned from this class is the diffusion and deep current, two type of current basically work in the semiconductor. And I also learned a new term which is quasi Fermi level. I never heard this term and quasi Fermi level, so I learned from this class. And I also learned the PN junction diode, how the PN junction format and how PN junction operation in forward bias and reverse bias. And I also learned about the built-in voltage and the avalanche breakdown and general breakdown also, and how the metal and semiconductor contact, like a Shockley contact or ohmic contact, and their phenomena I also learned from this clamp for the first time. And I also learned the basic operation of a MOSFET and degradation of the MOSFET and threshold voltage, and there are some effect of short channel effect, hot carrier effect, drain induced barrier lowering, and lightly doped drain source and halo phenomena, and how can we mitigate the short channel effect or hot carrier effect from the semiconductor. So this one I learned from this. So I really thanks to Professor J.U. Park and Professor Namyong Park to conducting this class. I am really enjoy it, and I'm very lucky guy. I think I to conducting or listening from him for nice lecture. So thank you all for listening.